Welcome. This screencast is going to look at questions 10 through 12 from Chapter 1, Section 1. And so 10 through 12, like number 9 and even number 8, kind of require that you have a good grasp of what this phase change graph means. So this is a case where we're putting energy into a system, and you start with a solid. It goes through its melting point because we're going this direction. If we were going the reverse direction, it would be called freezing point. And it goes through a liquid stage. And again, when it gets here, it goes through a boiling point when you're adding energy, or what we call condensing point when you're removing energy. And if you have it in some kind of closed system, then the temperature would continue to go up as it reaches its gas stage. So each of these phase changes is characterized by this plateau or this flat spot. So in this flat spot, what's important for you to realize is energy still going in or out. We'll look at this from the in direction. So energy is going in, but particles do not increase speed because temp remains the same. So if the particles had more speed, the average kinetic energy would increase, and we'd see an increase in temperature, but we don't. So where's the energy going? Instead, there's an increase in the interparticle distance, which is what's needed for the phase change to be complete. From a solid to a liquid, those bonds have to stretch enough for the liquid to be able to flow or move. And from a liquid to gas, now they have to stretch enough that they break free, and the intermolecular force, the particles are no longer close enough for the intermolecular force to affect one another. So number 10 says, explain why a burn to the skin caused by steam is more serious than a burn caused by the same amount of boiling water. So it's the same particles, but in one case, we've got boiling water. In the other case, we've got steam. So why is it more? Well, if you look, the boiling water is going to have plenty of energy. Boiling water is going to transfer energy. It's going to be warmer than you. It's hotter than your skin. So it's going to burn your skin as it cools, because the water is going to transfer that energy to you. So steam, why should that make it even worse? Well, because the steam is first going to condense. And remember, when we're going this direction, in order for steam to form, those particles have to slow down, so that energy has to go somewhere. So first of all, you get burnt from the gas losing energy to reform a liquid, and then you have hot liquid that continues to lose energy. So it's like you get burned twice by steam as opposed to just once by the boiling water. Number 11 says, which of the following occurs at the melting point when solid sulfur is converted to its liquid form? Movement of particles increases, or distance between the particles increases. And you're given the choice of one only, two only, both, or neither. And as I discussed earlier with number 11, it is going to be B, two only. The distance between the particles increases, but the movement of the particles, because temperature is remaining constant, the movement does not increase until the phase change is complete. Number 12, you're given a liquid substance at 80 degrees, told it has a melting point of 35 degrees, and asked to sketch, asked to take its temperature, regular time intervals while it cools to room temperature. Sketch the cooling curve. So I'm going to re-sketch this because it's going to be time versus temp. And since it's cooling, we're going to start hot, cool down, and it said it was a liquid, started at 80 degrees, so mark this as 80 up in here. And then we would expect to see at 35 it freeze. And it's a little misleading because they say melting point, but melting and freezing point occur at the same temperature. It's just a matter of whether energy is going in or out. And then at 20 degrees, because that's room temperature, unless you actually added ice to it, it would also plateau there. And I think the point they're making is a plateau doesn't necessarily mean there's a phase change. It could just mean the system has come to equilibrium with its surrounding temperature. So that's what number 12 should look like.